Alright, so let's get into our first proof. So as you can see, we've got a big square here with side length a plus b, and then we've got a smaller square here inside the bigger square, and it has side length c. How we are going to prove the Pythagorean theorem will be pretty simple. We know that all the shapes that make up this big purple square here are this red square and these four congruent right triangles. The Pythagorean theorem proof that we're going to do now is going to have to do with the sums of the areas of the red and yellow shapes being equal to the area of the big purple square. Let's get into it. We can find the area of the red square first, and since the side length of the square is c, the area is c squared. Then we can add 4 times the area of one of the congruent right triangles. Since there are 4 of them, we can just find the area of one and multiply that by 4. So we know the area of any triangle is half its base times height, so we can say half of AB. And that's going to be equal to the area of the big purple square. So we can just say that's equal to a plus b, which is the side length of the square. We can square it. So now we can just simplify this expression. The c squared is still going to be the same. That actually gives us plus 2ab. And then we've got this square here. And we get a squared plus 2ab plus b squared. So now we see we've got this common term here on both sides, positive 2ab, so we can just subtract that and cancel it out. And actually, you'll notice that this is beginning to look familiar. On the left side, we just get c squared. And then on the right side, we've got a squared plus b squared. Well, what do we know? This looks really familiar because this is the Pythagorean theorem. So this is the first proof of the Pythagorean theorem. And there are a ton of other ones. But in the meantime, that's the first proof. Now let's move on to the second one. So if you look here on the left, this is the picture that we just used to prove the Pythagorean theorem. The picture on the right here, we can actually get from the picture on the left. If you notice here, these two triangles are the same. Now if we take this triangle, this purple triangle down here, and we shift it up, we rotate it up, we can actually get it into this position. This orange triangle here is the same as this, and then we can take this red triangle here and once again rotate it up into this orientation. So now we've got all 4 triangles accounted for, and in their place, we've left these 2 squares here with side lengths a and b. So we've still got our 4 triangles, and now we've got 2 squares of side lengths a and b. This is a second proof of the Pythagorean theorem. So I'm going to draw a right triangle here. And it's a right triangle. The short leg, we can call it A, and the long leg is B. And then let's say the hypotenuse is C. So now I'm going to draw a congruent triangle like this. So it's congruent, so it's also a right triangle. the short leg is A, long leg is B, and hypotenuse C. And now I want to connect the two vertices like so to create a third triangle. And I can prove to you this orange triangle is a right triangle, because let's call this angle x. Since we know the sum of angles in any triangle has to be 180, and right now we have 90 plus x because of the right angle, and then we would need to have this angle be 90 minus x in order for the sum of all the angles to be 180. Since this is congruent, the same thing applies for the other triangle. X is between B and C, so B and C here, that means X is here. This line here, it has an angle measure of 180 degrees, and right now X plus 90 minus X equals 90, so this angle has to also be 90. So this orange triangle is a right triangle. Say I want to express the area of this total figure. Well, I could just write it as the sum of the areas of the two blue triangles plus the area of the orange triangle. So let's do that. The area of one of the blue triangles is 1/2 base times height, or 1/2 AB, and there's two of them, so multiply that by 2. Then I'm going to add the area of the orange triangle, which is 1/2 C times C, or simplify that to C squared. What is another way we can express the area of this total figure? Pause the video right now and see if you can figure it out. So hopefully you've thought about it, and hopefully you thought of this. This whole figure is a trapezoid. So we can just find the area of a trapezoid. We know the area of a trapezoid is the average of its bases times its height, or base 1 plus base 2 divided by 2 times the height. Base 1 would be A plus base 2, which is B, divided by 2 times height. This here is the height, which is the sum of A and B. So here we have an equation. Now we can simplify. On the left, 2 times 1/2 is just 1, so this is just AB, and the 1/2 C squared is fine. We can just leave it as is. Then on the right, we can multiply A plus B times A plus B. So that gives us A squared plus 2AB plus B squared, and it's all over 2. I have a 1/2 here and a 1/2 here, and I don't really like fractions. So I want to get rid of those fractions. I can just multiply both sides by 2 then. So let's do that. Multiply this by 2. Multiply the right side by 2. Then on the left, 2 times AB is 2AB. 2 times 1/2 C squared is going to be just C squared. And on the right, the denominator is cancelled out. So that just leaves us with A squared plus 2AB plus B squared. Finally, we can subtract and cancel out 2AB on both sides, leaving us with C squared equals A squared plus B squared, which again we recognize as the Pythagorean theorem. This is quite an elegant proof, and what makes it even more interesting is that this is actually a proof by a US president. And it's not a recent president, so you might not know who it is, but can you guess? The answer will come in 3, 2, 1. James Garfield. Yes, the US president submitted a proof on the Pythagorean Theorem, and this is his proof. If you thought this video was interesting, or if you learned something, consider liking and subscribing. Thanks for watching, and have a good day.